Year 13, Chapter 2, Trigonometry, Lesson 3, Small Angle Approximations. So, what do we mean by small angle approximations? Well, as always, we're going to start with the trigonometric graphs. Have a look at the graphs I've drawn here on the left-hand side. I have a graph of y equals sine x, and I have a graph of y equals tan x. Now, I also have a third graph, a straight line graph, which is the graph of y equals x. So it's important to remember at every point on the line y equals x, the x and y coordinates are equal to each other. Now, look at this region here, where the values of x are very, very small. They're smaller than pi by 6, which is this angle over here, and pi by 6 is about 0.5. Can you see that both the graph of sine x and tan x match the graph of y equals x very, very closely for these small angles, for these small values of x? So if I were to input a value of x here, for instance, and I were to input it into the function sine x or the function tan x, I would get an output which was very, very similar to my input. So let's take as an example, what would happen if x was equal to 0.2 radians? What would sine of 0.2 be equal to? Well, from my calculator, I can say it's 0.198, which means it's approximately 0.2. So this is what I was talking about. Sine of the input value is approximately the actual input value. And what about tan of 0.2? Well, my calculator tells me that's 0.202 ... so that is approximately 0.2 as well. So what we know is that for small angles, and we will define what we mean by small a little bit later on, sine x is approximately equal to x, and tan x is also approximately equal to x. Now, this doesn't work when angles become a little bit larger. Let's have a look here, for instance, at x equals pi. Now, you can see that sine of pi is equal to 0, and tan of pi is also equal to 0. So neither of these values are anywhere actually close to the value pi. So this is truly only an approximation that works when angles are very, very small. Now, over here, you can see I've highlighted the area in question in a little bit more detail. Now, this angle here is pi by 6 radians, which, as I've said, is approximately 0.5. So it's really up to this point here that we get a very good approximation. So let's summarise. Now, you'll find that the textbook tends to use theta for an angle rather than x, so I'm going to do the same. And what I'm going to say is that for small angles, or small values of theta, and again, we will define exactly what we mean by small values of theta a little bit later on, we can say that sine of theta approximately takes the value theta, and tan of theta approximately takes the value of theta. And it's really important that we know both of those two results. And what we're going to do in a minute is prove these two results. So we're now going to prove these results for small angle approximations of tan theta and sine theta. Please remember that throughout we are working in radians. This does not work in degrees. We have to be in radians so that the angle can be small enough for this to actually work. Look at my right angle triangle. I'm going to label this vertex O and this vertex T and this vertex P, and the distance from O to P is equal to a value of R. Now, I'm going to imagine that we draw an arc centred at O with a radius of R. Now, if we are to do that, then because the radius of that arc or that circle is of value r, that circle will pass through the point P. So we would have an arc that looks a little bit like that. So where this arc, which is part of a circle centred at O, intersects the line OT, we create a point of intersection which I will call Q. So PQ is an arc of this circle. Now, what's interesting is that there is a right angle here. And because OP is a radius of the circle and TP is perpendicular to the radius, we know from our circle theorems that the radius and the tangent are perpendicular at the point of contact on a circle, which means that PT is a tangent to the circle at P. Now I'm just going to put in a few more labels. Remember, Q is a point on a circle centred at O with radius r, which means the distance from O to Q is also equal to r, the radius. And I'm going to join point P to point Q with a straight line, i.e. with a chord, like that. And I'm also going to label this angle here, the angle in my right angle triangle, as theta. Now there are a number of different shapes here that we're going to focus on. Now the first thing that I'm going to do is to work out the area of the sector OPQ. Now we know the area of a sector formula in radians, and remember this whole thing will only work if we're in radians. The area of the sector OPQ is a half r squared theta. So that's the area bound by the two radii and the yellow arc from P to Q, the whole sector. Now, the next thing that I'm going to work out is the area of the triangle OPQ. Now, just in case anybody's not sure where that is, I'll highlight that in orange. So it's this triangle over here. It's bound by the two radii and the blue chord from P to Q. So it's slightly smaller in value than the area of the sector, which you can see has a slightly larger area. Now, how do we work out the area of a triangle? A half AB sine C. So a half multiplied by the two side lengths, so r times r, which is r squared, multiplied by the sine of the angle in between. So a half r squared sine theta. Now, the last thing that we're going to work out the area of is the area of the triangle OPT, which is the right-angled triangle. So that is equal to a half multiplied by the base, OP, multiplied by the height, which is equal to PT. Now, OP is simply the radius, so that's r. What about PT? How are we going to work out the value of PT? Well, look at your right-angled triangle, and we know that tan of theta is equal to PT, opposite, divided by the adjacent r, which tells me that PT is equal to r tan theta. So I can replace PT with r tan theta here. So this then allows me to write down a simplified version for the area of the triangle OPT, the original right-angled triangle, which is a half r squared tan theta. Now, what am I going to do with all of these results? Let's have a look. So now, what I want you to do is imagine that the angle becomes smaller and smaller and smaller. So imagine taking the line OT and bringing it down towards the ground, so T moves closer and closer to P, so the angle becomes smaller and smaller. Well, what's going to happen to these three shapes? The smaller triangle, the sector, and the larger triangle. So let's take a look at this. Here's our triangle OTP drawn again, but with a much smaller value of theta here. So this time, when the circle is drawn, we get this, and there's the point Q, and then when we draw in the triangle, we get this. Now, as theta becomes smaller, the three areas become closer and closer and closer together in value. So the sector, the two triangles have approximately the same area. So this means I can say that a half r squared theta, the area of the sector, is approximately the same as a half r squared sine theta, which is the area of triangle OPQ, and that's approximately the same as a half r squared tan theta, the area of the larger right angle triangle OPT. Now, looking at that statement there, we can cancel a half from each part, we can cancel r squared from each part, and then can you see what we're left with? We're left with the statement that sine theta is approximately the same as tan theta, and both are approximately the same as theta for small values of theta. And again, we will discuss specifically what we mean by a small value of theta more precisely a little bit later on. So now, having identified that sine theta and tan theta are approximately equal to theta for small values of theta, what about cosine? Let's have a look at the cosine function. Well, it's a lot harder to actually find anything out here, because if we look at small angles, there's no easy answer as to what any kind of approximation might be. So we're going to have to dig a little deeper in order to find out what the cosine function approximates to for small angles of theta. So I want you to consider a unit circle, i.e. a circle which has a radius of 1. Now I'm going to mark some points related to this circle. I'm going to mark the centre O. I'm going to mark a point P on the circumference here and another point on the circumference which I will call Q. Now, let me join O to P to create a radius there, the straight line, and let me join O to Q as well to create another radius. And remember, it's a unit circle, so both values of the radius are equal to 1. Now, I'm going to drop a perpendicular line from Q to the radius OP to create a right angle triangle OQ, and we'll label this point here R. I'm going to label the angle here, angle QOP, theta, and let's write down a few of the things that we know. So we know that OQ is equal to OP is equal to 1, the radius. Let's find the arc length here. I've highlighted it in green so you can see which part I'm talking about. So the arc length, PQ, is of course equal to r theta, but r equals 1, so the arc length PQ is simply equal to theta. Now, I also want to find out this distance here, RP. Now, that's equal to OP, take away OR, and we know that OP is equal to 1. What about OR? Well, what I'm going to do is I'm actually going to focus in on this right angle triangle in a little bit more detail. So what can I write down? I can say that the sine of theta is equal to the opposite, which is QR divided by the hypotenuse OQ, which means sine theta is equal to QR divided by 1, because OQ is 1, which tells me that QR is simply equal to sine theta. And I can do something similar with cos theta. Cos theta is equal to the adjacent OR divided by the hypotenuse OQ, which is just 1. So I can rearrange this and it will tell me that OR is equal to cos theta. So So that's quite useful coming back to here. OR is the same as cos theta. So I now know that RP is equal to 1 minus cos theta. Now you may be wondering why I've collected all these various pieces of information, but there is a reason for this. I'm going to draw in one last line here, and it's a chord that joins P to Q and creates a right angle triangle PQR. So what I'd like you to now do is consider the triangle PQR. And because it's a right angle triangle, I can apply Pythagoras' theorem to this, which tells me that PQ squared must equal PR squared plus QR squared. Now, there's a little bit more to this. When theta is small, and again we will come to the definition of what we mean by small a little bit later on, I want you to imagine Q getting closer and closer and closer to P because the angle theta gets smaller and smaller. I'll show this in a diagram. So you can see here Q has moved closer and closer to P, so that's because the angle theta has become smaller and smaller. And what happens when we draw in this chord PQ, what we can say is that the chord PQ becomes approximately the same in length as the arc PQ, which means it's approximately equal to theta, only when theta gets smaller and smaller. So you can see that the chord and the arc become approximately equivalent in length, and we know that the arc is equal in length to theta from up here. So how does this help us? Well, let's go back to our Pythagoras theorem statement over here. So we now know that PQ squared is approximately theta. So we can say that theta squared is approximately equal to PR squared. Now, where do we know about PR? Well, we worked it out over here because it's the same as RP. So instead of PR squared over here, I can write 1 minus cos theta all squared. And then the last part of this is QR squared. And I know about QR because I worked it out over here. So that's sine theta all squared, or sine squared theta, which is the neater way of writing it. So I have an approximation, and I'm going to simplify it. So this tells me that theta squared is approximately 1 minus 2 cos theta plus cos squared theta plus sine squared theta. And what do I have here? Cos squared theta plus sine squared theta, we know that's the same as 1. So this then gives me the result that theta squared is approximately equivalent to 2 minus 2 cos theta. Let's look at that in more detail. I can simplify this. So it rearranges 2 cos theta is approximately 2 minus theta squared, and dividing by 2, that tells me that cos theta is approximately 1 minus a half theta squared. And this is my small angle approximation for cos theta. Now let's test this out. I'm going to choose a small value of theta, of course in radians. Let's let theta equal 0.3, and let's work out what cos theta is equal to. So in radians, cos of 0.3 is equal to 0.9553, which makes sense, it's very close to 1, thinking about the cosine graph. Now, let's work out what 1 minus a half theta squared is equal to, which is the approximate value, according to the result that we have derived, and that is equal to 0.955. So look how close these values are. You can see it's a very good approximation for cos theta. So let's summarise the 3 approximations that we have found. If theta is small, we know that sine theta is approximately theta. Tan theta is also approximately theta, but cos theta is approximately 1 minus a half theta squared. Now you can see a moment ago I substituted in 0.3 and got an excellent approximation for cos theta. I've used 0.2 previously for sine theta and tan theta and also got very good approximations. But all three approximations are excellent when theta is between minus 0.1 and 0.1 radians. And remember, for any of these approximations to work, your angle has got to be in radians. Now, why might we want to approximate sine theta, tan theta and cos theta? Well, doing so can allow us to simplify a complex calculation. If we go back to eras of mathematics where people didn't have access to calculators or computers and they had to do trigonometric calculations, well, using a small angle approximation would allow somebody to be able to calculate something for a small angle without having to use any complex trigonometrical calculation, which couldn't be done very easily or as easily without using a calculator. We're going to have a look at a few examples involving small angle approximations in just a minute. So, first example, we're going to find an approximation for cos theta, take away cos 2 theta, when theta and 2 theta are both small. Don't worry about the numerical value of theta or 2 theta here. You've been told that they're both small, so that's all we have to work with. So, cos theta minus cos 2 theta is approximately, you must get the presentation of these sorts of problems correct. We want to use the approximately symbol, the wiggly equals sign. Well, we know that cos theta is approximately 1 minus a half theta squared from the work that we've just done. And we're subtracting from that cos 2 theta, which means I want to take this approximation and I want to replace theta with 2 theta in the approximation. Now, let's simplify this carefully. So it's 1 minus a half theta squared minus 1 plus a half multiplied by 4 theta squared. So I get a neat cancellation of 1 subtract 1 here, and the rest of this simplifies to give me 3 over 2 theta squared. So I know that cos theta minus cos 2 theta is approximately 3 over 2 theta squared. So I can use small angle approximations to take a more complex trigonometric expression and simplify it to something much, much simpler, but which will only work when theta is a small value. Now, let's look at example 2. It looks much more complex at the onset, but we can break this down. Now, what does this mean here? This bit of notation at the start. You've seen this before when you studied differentiation from first principles. It means find the limit of the expression in brackets as theta becomes smaller and smaller and smaller, i.e. as theta gets closer and closer to 0. So what we have to do is simply take the result in brackets and investigate it a little bit further. So what do we know about the statement in brackets? Well, you've seen the numerator before. It was in the first part of the question. It was in example 1. Cos theta minus cos 2 theta is approximately 3 over 2 theta squared, and it's being divided by theta squared. Now, you're going to carry out the division, and that leaves you with 3 over 2. So what happens as theta approaches to 0? Well, there is no theta left in this, so the limit has got to equal 3 over 2. Now, people sometimes find that last little bit a bit difficult to understand, so let me just give you another example down here, much simpler one. Find the limit as theta approaches 0 of 2 plus theta. Now, as theta approaches 0, effectively you allow theta to become 0, and anything that's unaffected by theta stays the same, so the limit of this expression in the blue brackets would just be equal to 2 once theta effectively becomes 0. In this expression over here, there was no theta left after we did the division, and so the final outcome was just the 3 over 2 left. So, example 3, part 1. Find an approximate value for sine theta plus tan theta when theta is small. So let's take a look at this. Sine theta plus tan 3 theta. Now sine theta is approximately theta. tan 3 theta will approximately be 3 theta. So this would then become 4 theta. Just as an aside, I'm allowed to put an equals sign here, full equals sign, because what I'm saying is that this line here is equal to 4 theta. If I were writing out the full thing again, I would say sine theta plus tan 3 theta is approximately 4 theta, a little quirk of mathematics. So part 2, a little bit like the previous question, we're going to evaluate the limit as theta approaches 0 of sine theta plus tan 3 theta over theta. So the limit of this as theta approaches 0, well, we can replace the numerator with 4 theta. Theta will cancel out, leaving us with 4. There's nothing dependent on theta anymore. Theta is already a small value. We've used the approximations up here to build the expression for theta. So the final answer is just 4. Now, it might be interesting as an aside to allow theta to equal a very small value. Let's say theta equals 0.1, and we're going to see what sine of 0.1 plus tan of 3 lots of 0.1, which is 0.3, all over 0.1 is actually equal to. Input it into your calculator, and you will see that it's equal to 4.091 ... So that is actually approximately 4. So you can see that this result does actually make sense. So example 4, we have the whole question as one package here. Find the limit as theta approaches 0. So this simply tells us we're looking at small angle approximations, because theta is getting closer and closer to 0, i.e. theta, the angle is getting smaller. And we've got 1 minus cos theta over 4 theta sine theta. So here's what I'm going to do. I'm going to put in the approximations for cos theta and for sine theta. So for cos theta, the approximation is 1 minus a half theta squared. And of course the approximation for sine theta is just theta. So let's work through this. This is the limit as theta approaches 0. Now in the numerator, what do I end up with? I end up with a half theta squared, and the denominator I end up with 4 theta squared. So this becomes the limit as theta approaches 0 of 1/8, and of course there's nothing dependent on theta anymore, so the limit is simply 1/8. Now again, you might find it interesting just to try a value of theta and see what we get. So I'm going to try theta equals 0.05, a really small value of theta. So we're going to work out 1 minus cos of this theta value over 4 theta multiplied by sine theta. So I'm going to input 0.05 and see what the calculator gives me. And my answer is 0.1250 ... And of course, you can see that's approximately 1/8. So it is a really good approximation because I've obviously subbed in a very, very small value of theta. Now, just as an interesting aside, imagine what would happen if I substituted in theta equals 10. That's not a small value of theta at all. So I would then replace theta with 10. What would I get when I do this? Well, I get an answer of minus 0.0845, which is absolutely nowhere near 1/8. So you can see that when theta is large, the approximation doesn't work.